Kin-Wang Kin-Wang Ng. My Cantonese is terrible. He's going to talk about his research on this Axions, cosmic parity violation and inflationary black holes. So probably not many people are familiar with this kind of research. Anyway, let's welcome Dr. Ng.
Come back here. Yeah, although a new building, we're all of us in the old building over there. And yeah, I originally from Hong Kong. This I use Cantonese for my name. So I teach you how to pronounce my name.
Okay.
It's John Ellis. You know John Ellis?
Yes.
Yeah. John Ellis taught everyone in a conference how to pronounce my name, just like I did. And hit your stomach hardly. Yeah. Okay. Everybody knows how to pronounce. And okay, since you talk about Hong Kong, there's Axions, cosmic parity violation, inflation black holes. The title is 无厘头. And I don't have an outline, so just follow me. Yeah. If you don't want to follow me, just take a nap. Yeah. And first of all, primordial black holes. And I hope at the end I will convince you, although it's 无厘头, but at the end everything is just boiled down to one single piece of physics, axions, and axion coupled to photon and so on. And we start with primordial black holes, and we if I follow the translation, it will be too long. I will jump here. Primordial black hole. Why? These days we come back to talk about primordial. Primordial black hole is really old stuff. Already 40 years old, before you were born. Most of you were born. And recently, especially in cosmology, as a cosmologist, we come back to primordial black hole because of LIGO. Everybody knows. Yeah. The LIGO, they detect 10 solar mass, 10 solar mass black hole. The 10 solar mass black hole, and a group of people just postulated that the LIGO, around 10 solar mass black holes are actually primordial. Primordial means it's different from astrophysical black hole. Physical black hole is some, I'm not expert to this, some star formation, this, and then evolve finally to the binary black holes, and then they merge to emit a gravitational wave. And so cosmology, no, wait, we don't like that scenario. Is there's another possibility? Those black holes are formed in very early universe, before, probably before Big Bang nucleosynthesis, for example. This is called primordial black hole. It's not astrophysical black hole, and this is we call primordial black holes. It formed in very early universe, and so if you're interested, you can go back to look at these papers. Yeah, and two of them are parallel. You can see there's some important thing pops up recently. And the interesting thing is the primordial black hole behave like a polar matter, and this 10 solar mass. And why is polar matter? Because they interact only gravitationally, and it's an ideal candidate for polar matter. And so you may have to imagine why it's cold matter, because it's quite heavy stuff. Yeah. Think about it. Yeah. When we are doing N simulation of the large scale structure, I think everybody has seen the movies about this formation of structures. And one dot, how heavy is it? It's 10 to the power 8 solar mass. This is the best resolution we can do now for the N-body simulation of the large scale structure. So and that's give you a feeling why primordial is so heavy is still a good candidate for Coulomb magnet. And again, and another interesting thing is primordial black hole is collapsed from baryonic matter. And we worry about if there's too many baryonic matter will spoil Big Bang nuclear synthesis, but no, because they are black hole, they won't participate in Big Bang nuclear synthesis. So that's evade the bound from the baryogenesis. Okay. Yes.
Already primordial black holes at the time of nuclear synthesis.
Yeah, before Big Bang nuclear synthesis. Yeah. And primordial black hole formation, and so there's some in the literature you can find form in phase transition. For example, quark-hadron phase transition, you can form at most the black hole of stellar mass. That is really at most. You cannot form 10 solar mass. So now we're interested in LIGO black hole, 10 solar mass. So this is not the good thing for us to produce primordial black hole. And now in this talk we will look at inflation. We make use of inflationary concept to produce black hole. In fact, there's a lot of papers about this topic, and it can generate primordial black holes over a very wide range solar mass, from supermassive, a billion solar mass, down to subsolar mass. So then you can say it's nothing. It's really a crazy model. Yeah, it's a crazy model, but it gives you whatever you want. Yeah. Although sometimes you need fine-tuning. Yeah.
But this, I'm a little bit confused. You see, this primordial black hole exists before the inflation?
No.
Just right after the inflation?
Inflation can produce this kind of primordial black hole.
Oh.
Yeah. And that's what we are going to.
But hadron were formed already at that time.
Inflation.
No, I mean in inflation stage, the hadrons already formed.
Not yet. Yeah.
Not yet.
We will come to
so
that.
just elementary particles exist.
Yes. Okay, and how to form primordial black hole of, for example, solar mass during inflation. I prepared the talk really targeted at the high energy people, so I didn't know that this is quite a general graduate student here. Yeah, I'm very sorry about this slide. And anyway, I hope you can learn something today. And this is the time. This is time. And the time of the universe. And this is the event of how far you can connect with each other. During inflation, the so-called horizon. The horizon is constant. Yeah, it's constant. It's quite odd thing about inflation. Yeah, and I cannot explain in such a short time. And during inflation, the horizon is a constant. It's a constant. And now that we are not very familiar with. And at this is the end of inflation. This is the start of inflation, and this is the end of inflation. And at the end of inflation, there's a called reheating. It will reheat the universe to a very high temperature, and it starts the Big Bang. This is the Big Bang. The Big Bang, the universe expanding, and that means the horizon is expanding. Okay, this is a very simple cartoon how to describe you the expanding universe, and also inflation before the so-called hot Big Bang in order to solve many so-called cosmological problems. Okay, how to produce primordial black hole? And is we mix something delta so-called perturbation, delta rho over rho. If the universe is homogeneous, you cannot form a black hole. you imagine you form a black hole, you need some uneven distribution of matter. And how uneven? You have to big enough in order for the black hole to collapse. If that roll is too small, the black hole, they don't have enough gravity to collapse to form a black hole. So the job for inflation for us is to produce enough delta rho over rho such that when delta rho over rho, there's a theory, when delta rho over rho exceeds the horizon. We look at that one fixed length scale. This is, for example, this is the scale of the present universe, the size of the present universe, or the size of a galaxy. This. If you look at the size of the size of the universe, if you produce large enough delta rho over rho, and from the theory, when this delta rho over rho exceeds the horizon during inflation, and the delta over rho remain a constant, there's some theory tell us that. And when we enter the horizon, and delta rho over rho, if it's big enough, they will collapse into a black hole. Yeah. Okay, this, for example, if we really produce at this length scale, large enough delta rho usually is about 1. And when this delta rho over rho we enter the horizon, the whole universe we see today will collapse into a black hole. This is the how inflation, how you make use of inflation to produce primordial black holes. And okay, we have taken the whole universe as an example, but we don't need to produce such a huge massive black hole. For stellar massive black hole, what length scale we should look at? This is the formula for how big the black hole will be formed when the scale we enter the horizon, and we count by the e-folding n. N is the e-folding before the end of inflation. Now we know that n have to be around 60 in order to solve cosmological problems. Why the universe so old, so big, and this is the duration of the inflation. We need 60 e-foldings. And this is the end before the end of inflation. Yeah, for example, if you can produce delta rho over rho 40 e-folding before the end of inflation, then you can produce a solar mass black hole. This is that's what we learned from this field graph.
So how about this the mass of but during the inflation period, right?
Yeah.
At these
this formula taking into account the mass. Okay, 40 is around here. If we can produce big enough delta rho over rho here, and when we enter in horizon, and this volume of mass will collapse into black hole, and how heavy it is, given by this formula. If you put in 40 here, then the mass is about 1 solar mass. That means if you produce delta rho over rho near the beginning of inflation, then when it collapses, it becomes a really, really huge black hole because the n is really big. Yeah. I think the talk too slow. Okay, stop it. Inflation. And from this large scale structure observation, did I put anything? No. The large scale structure and the CMB, the delta rho over rho, very small. Now we know that the uneven distribution of the matter at very large scale compared to the universe, what is the number? Delta rho over rho is 10 to the minus 5. Very small. I mentioned in order to form primordial black hole, you need delta rho over rho close to 1. So this is, and that's why there's a lot of model try to produce delta over rho compared to 1, but avoid this constraint. Let's see how. And we turn into interlinking inflation model. And just come back to this. I think it's better to use words more than the math to describe this. And everybody somehow heard about inflation and how to drive inflation. To drive inflation, we need a vacuum energy, and the vacuum energy is provided by the potential, inflaton potential. And this is the field. And this potential, look at the red line first. The red dashed line is a very simple quadratic potential. And this vacuum energy give you the latent heat to drive inflation. Drive inflation means the universe expand exponentially and driven by this vacuum energy. And the inflaton or the field will roll down, and then 1 eV, 2 eV, 10, 20, and 40, 50, and 60 eV when you roll down to the bottom. And this is the red dash line is a very famous quadratic potential to give us a successful inflation in order to solve the cosmological problems.
This is just a model, right?
This is just a model.
And this vacuum energy is just a 0 point energy.
0 point energy, you can see. It's 0 point energy. Yeah. And you put in a vacuum energy in Einstein equation, if you give you the radius of the universe will expand exponentially with time. And the red dash line is successful. It gives you 60 eV loading, and also at the beginning, we see if the rotation is rolling down, and the universe. Look back this one. Here, the inflaton is rolling down, and when it's rolling down, when we observe the large-scale structure of the present universe, you will see when all the way to the beginning of the inflation. We make measurement of the large-scale structure, and we will probe all the way to the beginning of the inflation. And what is the delta rho over here from prime measurement, from large-scale structure measurement? The delta rho over rho here is 10 to the minus 5. We have seen that already. So that means for this first 7 or 10 eV foldings, and it corresponds to the large-scale structure, the delta rho over rho cannot be big, and you cannot form primordial black hole during the first 7 or 10 eV because we have constraint from large-scale structure measurements, from CMB observation. The delta rho over rho have to be 10 to the minus 5, too small to form a primordial black hole.
So you're saying that they start to collapse only after we enter
Yes.
the horizon.
Yeah.
So there's really no black hole, during nucleosynthesis. You have black hole only much later.
But if you can form here, then it will we enter horizon, then it form black hole, and nucleosynthesis is about here.
So when you say you form it, it's before collapsing. So in what sense is formed? What do you mean you have a black hole?
No, not black hole here. Black hole is here.
Right.
We form a black hole here.
So you don't really have a black hole?
No, I don't have it now. No, it's just a seed for forming a black hole.
Okay.
Just to produce a seed,
the fluctuation
The
then
fluctuation.
become a black hole.
Yeah, become a little
During
at the
inflation.
when we enter the horizon.
Okay.
Okay, thank you to clarify this. All right. Okay, this is the model. This is the model we modify. It's kind of model dependent, but it's interesting to us. And we modify this the well-known quadratic potential into the bullseye. And also, why do we need to modify like this? And we need to change the delta over rho. This is our goal. And if we just modify the potential like this, it still gives you very small delta over rho. Yeah. And that's axion come into play. And we need something else.
Well, a very naive question.
Yeah.
Why do we really need this primordial black hole?
Why do
Yeah.
we really need?
Yeah,
I
just
in the
don't
first slide,
understand.
I said the primordial, the LIGO black hole could be primordial black hole.
But it's not confirmed, right?
It's not often. No, it's not
Okay.
confirmed. It could be an astrophysical black hole. Yeah.
But I thought you said someone told me it's because you see many very large black holes, and those could not have formed within, if it were not.
Yeah, it's another.
Supermassive.
Yeah,
black holes.
it's a problem. I mean, astrophysical problem
Okay,
to give us such a heavy. Okay. So I said modify the potential is not good enough to give you a big enough delta over. And what is the next we can do? We couple the inverton. The inverton now is an axion here. Yeah, there's a lot of string express here. There's a lot of U1 global symmetry in string, and the book can they give you the Gaussian boson and the axion. So that's a lot. If you don't believe me, ask. So this is the inverton potential, and this is an axion, and the axion coupled to photon. The coupled to photon, and that's why I draw the cartoon here, where the inverton roll down the potential, it becomes steep here, and the speed of the inverton become big. And in this particular model, when the speed of the inverton is big, it could produce a lot of photon. Believe my statement. I don't want to go back to this math. Yeah, yeah. And we call this a spinoidal instability. Yeah, when the speed of the inverton is big, it can produce a lot of photon. And one, I would say before that, one of the polarization of photon called right hand become tachyonic. The mass of the photon of this right hand neutrino is proportional to the speed of the inverton. So if the speed of the inverton is bigger, the mass become more negative, and you can produce the right hand photon easily. And this is isotropy too here.
Is
Yeah.
there some assumption about how it's coupled to photon?
The phi FF tilde, the Chern-Simon term. That's all. So you have axion and the potential, the potential and the Chern-Simon term, the phi FF tilde. Oh, okay, good. Yeah. This is the maybe it's good to go back a little bit. This is how you solve the photon mole function, and this is standard ENM, the standard. This one is standard, and this is the mole function of photon. And with the coupling, you have an additional term, and this Cassi parameter is proportional. I say proportional to the speed of the inverton. If the speed becomes big, one of the handedness becomes tachyonic. The mass becomes negative, and you can produce the cation easily. And this is the Cassie parameter. Remember, the Cassie parameter is proportional to the speed of the inverton. And you can produce a lot here. And this is this is the e-voting. This is the beginning of the inflation. And this is the end of the inflation. And the scalar field, the axion, start with value 12 pascal and roll down as standard inflation. And this one gives you the large scale structure. The seed delta overall close to 10 to the minus 5 for large scale structure formation. This is a standard inflation. But somehow at around e-voting 40 before the end of inflation, and in that particular model, and at that particular moment, you produce a lot of photon because one of the hand become tachyonic. You can produce a lot of photon at this moment, and then there's a back reaction. The production of the photon will hold the motion of the inverton. And you can see at this particular moment, the inverton is slowed down a lot and remain a constant almost at 5. And after that, it will down to the end of inflation. And the blue line is the Cassie parameter. You don't need to. So this is actually a very nice model to realize so-called the trap inflation. We always heard about you need a very flat potential to give you a successful inflation, but it's not necessary. For example, in this so-called trap inflation, you have a steep potential, but you can, if the inverton interact with photon, it will effectively slow it down, and the whole process really like a slow roll inflation. And this is the example. It's just, and this is standard, but because we don't want to spoil the nice first 10 e-voting, because we have a lot of constraint. Yeah, so we don't want to spoil. But after 10 e-voting, you can do whatever you want, essentially. And this is the trap inflation model. Okay, then how is it back home? And this is the e-voting. This is the beginning of the inflation. This is the end of the inflation. And this is delta overall. I don't want to really give you how to calculate, but just believe my number. And at the beginning, this is squared, delta overall squared. I said in the beginning of the inflation, we have to obey the Planck data, so you have to be 10 to the minus 10 for the first 10 e-voting. Yeah, in this model, yeah, we satisfy the Planck data. And I said, we play around. After that, you can do whatever you want. Yeah, in this particular trap inflation, I can produce because of huge photon production. And because of production, and there's a back reaction on the inverton, it can produce a big delta overall, or delta phi over phi. And this is why you can produce a big, huge delta overall, and then go back to the useful inflation. This particular model can give you a huge delta overall at around 40. And this length scale, we have learned that is correspond if we will give you the seed for the formation of primordial black hole of 10 solar mass. And this is the.
So you cannot tune the propagation.
Can, yeah, whatever you want. Yeah.
Oh, you can.
You can.
Yes. So it doesn't have to be at 40.
Yeah. Oh, you have to be at 40 in order to have 10 solar mass.
Oh, right.
Yeah.
Okay.
Yeah. Okay, and what you may ask, well, what's this? This is the constraint, the translation of the constraint on primordial. We have many